Imagine you're driving a modern electric SUV on the highway. You're cruising along at, maybe 75 miles per hour.
Right.
And you decide to pass a large semi-truck. So you press the accelerator, expecting that really smooth, instantaneous EV power.
Yeah, that immediate torque.
Exactly. But instead of speeding up, the motor controller deep inside the chassis it gets violently confused by this microscopic sensor error.
Oh, yeah.
And in a fraction of a second, instead of applying forward torque, it applies maximum braking torque to the rear wheels.
Which is terrifying.
Right. Your car literally tries to throw itself in reverse while doing 75.
It is, it's a genuinely terrifying scenario. And I think the scariest part is that the physical drivetrain might be completely intact. Like nothing snapped.
Right.
Nothing broke in the traditional sense. You are basically dealing with an invisible ghost in the machine.
And that ghost is exactly what we're hunting today. Welcome to another deep dive. Whether you are an automotive engineer prepping for a massive design review or a manufacturing specialist optimizing the factory floor.
Or even just a deeply curious learner.
Yeah, exactly. If you want to understand exactly what stops a modern electric vehicle from violently misinterpreting its own speed and torque, this deep dive is custom tailored for you.
The source material we are unpacking today is, well, it's incredibly dense. It's this uncompromising engineering documentation detailing what's known as the A09 motor resolver offset error.
A09.
Yeah. And this is a failure mode that sits at the absolute pinnacle of automotive risk.
We're talking ASIL D functional safety here.
Exactly. ASIL D, for those who, don't spend their days reading ISO 26262 functional safety standards.
Those is most people, I assume.
Right. Well, ASIL D is the highest, most stringent level of safety classification. It means a failure here poses an immediate life-threatening risk to the occupants. Yeah. So things like steering, braking, and unexpected motor torque, those are all ASIL D.
Okay, let's unpack this from the ground up. Because to understand this A09 error, we really have to visualize the heart of the EV, which is the motor itself.
Right.
So we have a stator, which is the stationary outer ring generating a rotating magnetic field.
Yep.
And inside that, we have the rotor, the spinning part that's packed with permanent magnets. And to make the car move forward efficiently, the magnetic field of the stator and the magnetic axis of the rotor have to be in a perfect, mathematically precise orthogonal relationship.
Orthogonal meaning exactly 90 degrees to each other.
Okay.
When that magnetic push is exactly perpendicular to the rotor's magnetic axis, you get maximum torque. It's, think of it like pushing a revolving door.
Oh, I like that analogy.
Right, so you want to push at exactly 90 degrees to the glass to get the most leverage. If you push at an angle, you're just wasting energy, basically compressing the hinges.
You're just shoving the door into the center pillar.
Exactly. It doesn't move the door, it just stresses the hardware.
And the piece of hardware responsible for making sure the computer knows exactly where that rotor is so it can time that 90-degree point perfectly is called the resolver.
Right. The resolver is essentially a highly precise rotary electrical transformer. It sits right on the end of the motor shaft.
Okay.
And it doesn't just measure speed. It measures the absolute angular position of the spinning rotor down to like fractions of a degree. And then it feeds that raw data back to the motor controller.
So if the resolver loses its place, the computer loses its place, which is where the entire system starts to unravel. The sources outline four distinct physical and sort of physical adjacent root causes for why this happens. Let's start with the first one, which is mechanical slippage and runout. We're talking about the physical reality of a motor vibrating itself to death.
Yeah, and if we connect this to the bigger picture, you have to remember that an electric motor doesn't exist in a pristine laboratory.
No, it's on a highway.
It lives in a brutal environment. It is subjected to relentless, long-term mechanical vibration. Potholes, rumble strips, and just the sheer rotational force of spinning at 15,000 RPM.
Wow.
And on top of that, it goes through massive thermal cycling.
Right, because you floor it onto the highway, the internal temperature spikes. Right. And then you park it in the snow, and it drops below freezing.
Precisely. And all the metals inside the motor, the steel shaft, the copper coils, the aluminum housing, they all have completely different thermal expansion coefficients.
So they expand and contract at totally different rates.
Yeah. Over years of driving, this immense repetitive stress causes microscopic shifting. You get eccentric installation issues, axial tilt, and even the the micro-loosening of the fixing screws holding the resolver in place.
So the resolver actually physically slips from its original 0 point.
Yes, so the computer thinks the rotor is pointing perfectly north because that's what the sensor is reporting. But the sensor housing has actually vibrated, say, a millimeter to the left.
Wow.
The physical reality has essentially drifted from the digital reality.
Okay, it's like the steering wheel of your car becoming slightly detached from the steering column.
Oh, yeah, exactly.
You think you're pointing the wheel straight ahead, and the sensors read dead center, but underneath, the physical tires have just drifted to the left.
That is a great way to visualize it. But the terrifying thing is, in an electric motor, the consequences of that drift are subjected to a mathematical multiplier that makes it infinitely worse.
Okay, wait.
And this is the second root cause from our source. It's called the pole pair multiplication effect.
Hold on. If I have a physical steering wheel drift of 1 degree, my tires are off by 1 degree, why does it multiply in a motor? What's the physical mechanism there?
Well, what's fascinating here is the difference between mechanical degrees and electrical degrees.
Okay.
An EV motor isn't just one giant magnet spinning inside another giant magnet. To generate massive torque smoothly, the stator and rotor are divided into multiple alternating magnetic poles.
Right, so north-south, all the way around the circle.
Exactly. And our source uses a very specific, terrifying mathematical example for this. A 20-pole motor.
20 poles. So that means it has 10 pairs of north and south poles.
Right. And because of this geometry, one full 360-degree physical rotation of the motor actually contains 10 complete 360-degree magnetic cycles.
Oh, wow. So the electrical math is cycling 10 times faster than the physical metal is actually spinning?
You've got it. So let's say thermal cycling causes a tiny, barely measurable 1-degree mechanical slip of that resolver. A 1-degree physical error.
Okay.
You have to multiply that by the 10 pole pairs. That microscopic 1-degree mechanical slip instantly mathematically multiplies into a massive 10-degree electrical error in the control system.
Wait, really? Just from 1 degree of slip?
Just 1 degree physically becomes 10 degrees electrically.
So the controller thinks the magnetic field is 10 degrees away from where it actually is.
Yeah.
What does that actually do to the power? I assume the efficiency just drops.
It is far worse than an efficiency drop. It causes severe DQ axis cross-coupling.
Okay, DQ axis cross-coupling. Let's break that down for the listener. The D axis and the Q axis.
Right. So in advanced motor control theory, the software mathematically splits the 3-phase AC current into 2 distinct vectors. This lets it control the AC motor like a simple DC motor.
Oh, wait.
The D-axis, or direct axis, that controls the magnetic flux. It's the strength of the magnetic field. The quadratus, or quadrature axis, that controls the actual torque. The twisting force that physically moves the car.
So one builds the magnetic foundation and the other does the actual pushing.
Exactly, and they need to be perfectly decoupled. But when you have a 10-degree electrical error, the math cross-couples. The controller just gets completely confused about its angles.
Because it's off by 10 degrees.
Right. So it starts accidentally dumping your torque-generating current into the flux axis, and it dumps your flux current into the torque axis.
So it's trying to push the revolving door, but instead of pushing the glass, it's just shoving the center pillar as hard as it can.
Yep. And the source data is incredibly precise on the consequence here. A 10-degree electrical offset causes the motor to instantly lose 1.52% of its torque output under the exact same command. But it doesn't just lose power. Because the current is going to the wrong places, it creates abnormal phase currents. The motor is literally fighting its own magnetic field.
Which means all that wasted electrical energy has to go somewhere. And, in physics, wasted energy usually equals heat.
Massive, dangerous overheating. The silicon carbide chips in the inverter are pumping hundreds of amps, trying to achieve a torque target that the offset error makes mathematically impossible. It just becomes a cascading thermal failure.
And all of that stems from a physical screw backing out 1 degree.
Yep.
But the third root cause in the source document has nothing to do with physical vibration or screws at all, right? It's completely invisible. It's the human element, commutation data loss.
Yeah. This is where the service bay becomes a liability. Imagine an aftermarket technician opens the motor to replace a bearing. They do a beautiful mechanical job. They torque every bolt perfectly to spec.
Yeah.
The resolver is physically pristine. But they forget to run the motor commutation calibration sequence on their diagnostic laptop before handing the keys back to the customer.
Oh.
Or, as the source points out, It can even happen at the factory if an automated flashing station accidentally uploads a generic nominal value software package instead of the highly calibrated bespoke software package meant for that specific motor's serial number.
So in either scenario, the motor controller is now using old, invalid software offset data to drive subtly different physical hardware.
Exactly.
See, this is what I find so wild about modern engineering. You can have a motor block bolted together to the millimeter, torqued to absolute perfection, physically indestructible. But a simple software flash version mismatch can cause the entire physical control logic to collapse at highway speeds.
It collapses because the controller is completely blind without its calibration file. Look, every single manufactured resolver has a tiny microscopic variance from the factory line.
Right, nothing is perfect.
Right. So the calibration file tells the software, hey, on this specific motor, true zero is actually at 0.02 degrees. If you wipe that data, the controller assumes zero is exactly at zero.
Which it never is.
Never.
Mm-hmm.
So the stator and rotor fields will never achieve that perfect 90-degree orthogonal relationship. The system reads the sensor, realizes the physical reactions make absolutely zero mathematical sense, panics, and triggers a protective shutdown.
Wow. Which brings us to the fourth and final root cause dimension. And this one feels almost unfair, honestly, because it happens even if the hardware hasn't slipped and even if the software is perfectly calibrated.
Right, thermal saliency and eccentricity.
Yeah.
This is what happens under extreme punishing loads. Say you're towing a heavy trailer up a massive mountain incline in 100-degree summer heat. The motor is demanding maximum current for a sustained period. This causes deep magnetic saturation in the stator and rotor cores.
Okay, magnetic saturation, let's dig into that. That basically means the steel core of the motor has absorbed absolutely all the magnetic flux it can physically handle, right? All the microscopic magnetic domains in the metal are completely aligned, and it just can't take anymore.
Exactly right. It hits a physical limit. And when metal hits deep magnetic saturation, the magnetic field in the air gap, that tiny millimeter-thin space between the spinning rotor and the stationary stator, it stops behaving linearly. It distorts. It warps.
So what does that do to our resolver sensor?
Well, the resolver relies on reading a pristine, perfect sine wave of voltage to calculate the angle. But under massive thermal and magnetic load, that sine wave degrades. It gets noisy and messy. And this causes what engineers call a dynamic zero shift. The magnetic zero point actually moves under extreme heat and load purely due to physics, even if the physical sensor is still bolted down perfectly tight.
Wow. It's like a magnetic mirage.
Yes.
The sensor is looking at the exact right spot, but the heat is bending the light. Or in this case, the magnetic flux, so the zero point appears to be somewhere else.
A magnetic mirage is a brilliant way to phrase it.
Yeah.
And you have to combine that thermal mirage with cumulative geometric manufacturing tolerances.
Because no physical object is perfectly round.
Exactly. There is always a microscopic wobble.
Right. The force refers to this as static and dynamic eccentricity.
Right. So as the slightly less than perfect rotor spins, the air gap is minutely wider on one side than the other, and that wider spot rotates with the shaft. This non-uniform air gap scrambles the magnetic density, which feeds corrupted, skewed data back to the resolver to digital converter, or RDC.
Okay.
So the angle decoding gets totally skewed by the physical wobble combined with the thermal mirage.
So what does this all mean for the engineers? We have a catastrophic failure that can be triggered by, a physical screw vibrating loose, or by a mechanic forgetting to click calibrate on a laptop, or simply by the laws of thermodynamics and magnetic saturation when you tow a boat up a hill. You can't just put a stronger bolt on it and call it a day.
No, hardware alone cannot save you here. When the root causes span physical loosening, human software error, and fundamental thermodynamic physics, you need a system that constantly watches its own back.
Which means we need to move from the physical problem into the digital immune system, the real-time diagnostic architecture.
Yeah.
Because the overarching mandate here is ASIL D functional safety, and the source document draws a very hard line in the sand, a fault-tolerant time interval, or FTTI, of under 60 milliseconds.
That 60 milliseconds is the magic number. It is the absolute maximum time allowed from the moment the magnetic field slips to the moment the car safely intervenes.
Wow. Less than a tenth of a second.
The system has less than the blink of an eye to detect that the motor is mathematically tearing itself apart, diagnose the root cause, and deploy a safety net before a catastrophic hardware failure occurs.
So how does a computer actually do that? How does it know its own sensors are lying to it? It starts before the car even moves, right? With a process called resolver offset learning, or ROL.
ROL is the crucial boot sequence. It happens every single time the motor is powered up, but is still completely stationary. The power control system, the PCS, performs this sort of covert diagnostic handshake. It injects a very specific high-frequency voltage signal into the stator windings.
Wait, if the motor is completely stopped, why are we injecting voltage? Doesn't that make it try to spin?
That's exactly why they use a high-frequency signal. It oscillates so fast that the heavy mechanical rotor doesn't have time to physically react and spin.
Oh, I see.
Instead, the computer injects this pulse and it listens carefully to the tiny electrical current that bounces back.
What is it listening for exactly?
It's listening to the motor's saliency effect. The rotor isn't magnetically uniform, right? It has permanent magnets embedded in it, meaning the inductance, the electrical resistance to changes in current is different depending on exactly which angle the rotor is parked at.
Okay.
By analyzing that tiny response current, the computer can mathematically deduce the exact true physical position of the rotor.
Oh, wow. It's like a submarine sitting in the dark, sending out a high-frequency sonar ping.
Yes.
And it listens to the sound wave bounces off the ocean floor to figure out exactly where it is without needing to turn on the headlights or move an inch.
That is a phenomenal analogy. It pings the rotor. And once it calculates that true physical position, it compares it to what the resolver claims the position is. The difference between the two is the exact offset.
Got it.
The system takes that newly calculated offset and writes it into non-volatile memory, completely wiping out any manufacturing tolerances, thermal shifts from yesterday, or software calibration errors. It sets a perfect, customized zero baseline for that specific drive cycle.
Okay, so the submarine knows where it is before it moves. But once you start driving, you're hitting potholes, you're heating up the metal, the magnetic mirage is happening. A baseline at 0 RPM doesn't help you at 10,000 RPM. How does it monitor itself dynamically while you're moving?
Well, that requires real-time offset checking. The software runs a continuous background algorithm while you drive. And one of the primary methods is monitoring the D-axis parasitic power loss during steady speeds.
Okay, back to our D-axis and q-axis. The D-axis builds the magnetic flux, the q-axis applies the torque.
Right. So when you are driving at a steady 65 miles per hour on a flat, unloaded highway, the motor control dynamics are very stable. In a perfectly aligned, healthy motor, the unloaded to axis current should perfectly match the computer's theoretical commands. It should be relatively constant.
Right.
But if the physical resolver vibrates loose while you are driving, the measured angles misalign. The controller gets confused and starts accidentally bleeding your torque current into the flux axis.
That cross-coupling effect we talked about earlier.
Exactly. So the diagnostic observer algorithm sits there just watching the D-axis. If it suddenly sees a massive unexpected spike in D-axis current that doesn't correspond to you pressing the accelerator, it instantly knows there is a zero offset error. It realizes the physical reality is no longer matching the sensor data.
That is so clever. And the source also details a secondary dynamic check used at lower speeds, right? Dynamic BEMF checking, being back electromotive force.
Yeah, back electromotive force is a fundamental concept of electromagnetism. It's essentially Lenz's law in action. As the permanent magnets on the rotor spin past the copper coils in the stator, they act like a generator. They generate a voltage that literally pushes back against the current that the inverter is using to drive the motor.
Wait, so the motor is simultaneously acting as a motor and a generator at the exact same time?
Always.
Wow.
And the diagnostic system uses this to its advantage. It samples the real physical phase angle of that natural back EMF pushing back from the motor. It then compares that natural angle to the target excitation angle commanded by the field-oriented control, or FOC, algorithm.
Oh, so it's comparing the physical reality of what the motor is naturally generating against the digital theory of what the computer is telling it to do.
Precisely. And the tolerance for error here is razor thin. If the real BEMF angle and the target FOC angle mismatch by more than 2 electrical degrees, the system immediately flags a catastrophic fault.
Just 2 degrees.
2 degrees is all it takes.
Okay, so the sonar ping worked, the dynamic checks worked, the digital immune system has caught the disease, it knows the resolver has slipped, the angles are cross-coupled, and the motor is a fraction of a second away from tearing itself apart. The FTTI clock is ticking. 60 milliseconds. What is the actual fallback mechanism?
This is where the engineering gets absolutely breathtaking. It initiates the ASIL D multi-level sensorless fallback.
Multi-level.
It's a tiered safety net that triggers based on the severity of the measured deviation.
Okay, the source divides this into soft redundancy and a hard safety clamp. Let's look at the soft redundancy first. How does it handle a minor slip?
If the offset deviation is detected to be relatively small, say, less than or equal to 5 electrical degrees, the system enacts a limp home mode.
Right, limp hum.
It immediately chokes the motor torque to a maximum of 30% of total capacity and hard caps the motor speed at 3,000 RPM.
So it nerfs the car so it can't hurt itself.
Yes. It gives you just enough regulated power to safely pull the SUV over to the shoulder of the highway, but prevents the massive cross-coupling currents from melting the inverter.
But what if it's not a minor slip? I mean, what if you hit a massive pothole, a bolt snaps, and the resolver housing physically rotates 15 degrees instantly?
Then limp home mode is completely useless because the sensor data is entirely toxic. It's actively feeding the controller poison. So within 5 milliseconds, which is a fraction of a single motor rotation, the control system executes a hard switch. It completely abandons the physical resolver. It stops listening to the hardware entirely.
Wait, it just cuts off the sensor.
Completely.
So how on earth does it know where the rotor is?
It seamlessly switches on the fly to a sensorless control mode. It replaces the physical hardware sensor with highly advanced mathematical models. Specifically, the source cites the use of an IC-SMO combined with MRS.
Okay, those are massive acronyms. We need to break those down. ICE-SMO, what does that math actually do?
ICE-SMO stands for Improved Super Twisting Sliding Mode Observer.
That sounds like a sci-fi weapon.
It really does. It's a brilliant piece of control theory. An observer in engineering is an algorithm that estimates the internal state of a real-world system by looking at its external inputs and outputs. Since it can no longer see the rotor angle from the sensor, the IS-SMO looks at the voltage going into the motor and the electrical current coming out.
And it calculates the difference.
Exactly. It uses the difference between the expected current and the actual measured current to mathematically back-calculate exactly where the rotor must be. The sliding mode part means it forces the mathematical estimation to slide along a predefined mathematical surface towards the true state.
So it's constantly self-correcting.
Making it incredibly robust against sudden disturbances, it constantly corrects its own errors in real time.
Okay, and MRIS?
Model Reference Adaptive System. The computer has a perfect theoretical mathematical model of the motor, the reference model. Then it has an adaptive model that is constantly tweaking its own parameters based on the real-world current feedback.
Yep.
When the outputs of the two models match, the system knows its estimated rotor angle is correct.
Okay, if I'm trying to visualize this, it's not like an airplane flying by the stars, because that requires seeing external sensors. It's more like waking up in your own house in pitch black darkness.
Right?
You can't see anything. But you know the layout of your house. That's the MRAS reference model.
Yes.
And as you walk, you use your muscle memory, the IST-SMO equations, and you feel the physical resistance of the floor and the walls bumping against your hands. That's the current feedback.
That's perfect.
Combining the layout in your head with the physical feedback of the walls, you can navigate the dark house perfectly without ever using your eyes.
That is a phenomenal, perfectly accurate analogy. The math is literally feeling the resistance of the electrical current to know exactly where the spinning magnets are in the dark.
But if you're sprinting through the dark house at full speed, muscle memory might not be fast enough. What if the math fails?
Yeah.
What if you were doing 80 miles an hour, the sensor breaks, the math tries to take over, but the motor is spinning at 15,000 RPM, and the equations just can't lock on to the current feedback fast enough?
That is the ultimate nightmare scenario, and the engineering answer is violent but necessary. This is the hard safety clamp.
The hard clamp.
If the sensorless switch fails to lock on at high speeds, you have a massive permanent magnet motor spinning wildly out of control. And because it's acting as a generator, it is pumping massive, unregulated, chaotic voltage back up into the car's electrical system.
And that FTTI 60 millisecond clock is almost out.
You have milliseconds to prevent an electrical fire.
So the system triggers what the source calls a stepwise ASC. Active short circuit. Wait, it deliberately shorts out the motor. Doesn't that destroy it?
It is a calculated sacrifice to save the rest of the car. It happens in 2 phases. Phase 1 executes in exactly 1.5 milliseconds. The inverter forces a 2-phase short circuit. It connects 2 of the 3 motor wires directly together.
Why only 2?
This acts as a softer initial clamp to suppress the massive transient overcurrent spike so it doesn't instantly blow the power electronics to pieces.
Oh, I see. It absorbs the initial punch.
It absorbs the punch. Then, a few milliseconds later, phase 2 engages. It transitions to a full 3-phase lower bridge short circuit. It completely locks the motor down electrically.
Wow.
All the electrical energy is trapped circulating safely inside the heavy copper windings of the motor, rather than shooting back into the car.
And the data point in the source says this brutal clamping procedure is specifically designed to keep the DC bus voltage safely under 720 volts. Why 720?
Because 720 volts is the absolute physical ceiling for the components in this specific architecture. If the unregulated voltage from that spinning motor spikes above 720, you experience EOS, electrical overstress.
Which means?
The incredibly expensive silicon carbide chips in the main inverter will physically melt. The high-voltage wiring harness will ignite.
Oh, man.
The stepwise ASC sacrifices the smooth driving experience, pops a massive electrical parachute, keeps the voltage under 720 volts, prevents a catastrophic fire, and allows the heavy mechanical mass of the car to safely glide to a halt.
It's a spectacular safety net. But, if you're listening to this and thinking, wow, the math and the parachutes are amazing, but wouldn't it be better if the hardware just didn't fail in the first place?
Exactly.
Which is exactly what I was thinking. If you're thinking that, you are thinking like a DFMEA engineer, design failure mode and effects analysis. The philosophy is, don't just build a better net to catch the failure, design the physical hardware so the flaw is physically impossible from day one.
Which is exactly what the engineers did next in our source. And the first preventative design standard is beautifully simple. It's a mechanical poka-yoke.
Poka-yoke being the Japanese manufacturing philosophy of idiot-proofing a design so just cannot be assembled incorrectly.
Precisely. The design standard strictly mandates that you cannot just bolt the resolver housing to a flat surface and hope the friction of the screws holds it against vibration. The interface must have a dedicated, high-precision machined keyway or a geometric positioning step pin made of solid steel.
So there's a physical metal groove on the motor and a solid steel pin on the sensor that slots tightly into it.
Yeah.
The resolver physically cannot rotate out of alignment unless the rotational vibration forces are strong enough to literally shear solid steel in half.
Exactly. And they don't stop at just adding a pin. The tolerance stack-up, which is the combined dimensional imperfections of all the manufactured parts assembled together, is strictly, rigidly locked. The source document dictates that the rotor runout, or TIR total indicator reading, must be held to less than or equal to 0.05 millimeters.
Let's put that in perspective for a second. 0.05 millimeters. A standard sheet of copy paper is about 0.1 millimeters thick.
Right.
They're restricting the physical wobble of this heavy, spinning metal mass to less than half the thickness of a sheet of paper.
Yeah, and by restricting the physical assembly to 0.05 millimeters, they essentially eliminate the physical possibility of the mechanical slippage we discussed in the first root cause. The metal simply has no physical room to move or build up eccentric momentum.
But wait, earlier we talked about thermal saliency.
Yeah.
The issue where extreme heat and magnetic load bends the magnetic field, creating that magnetic mirage that shifts the 0 point, even if the physical sensor hasn't moved a micrometer.
Yep.
A solid steel pin and a 0.05 millimeter tolerance can't fix an invisible magnetic distortion.
You're absolutely right, they can't. You can't fix thermodynamics with a steel pin. To fight thermal saliency, the designers implemented algorithmic decoupling. They embedded a high-resolution 2D inductance lookup table, or LUT, directly into the primary control software.
How does a lookup table fix a magnetic distortion? It's basically just a massive cheat sheet for the computer, right?
Yes, it's a massive multi-dimensional grid of data. During the R&D phase, engineers put the motor on a dyno and map out exactly how the motor's magnetic field distorts at every single possible combination of temperature, RPM, and current level. They bake that map into the LUT.
Ah, I see. So in the real world, when you're towing that trailer up the mountain and the motor hits deep magnetic saturation,
the software checks the table in real time. It sees the temperature, it sees the current load, and the table tells it, hey, under these exact conditions, physics dictates that the magnetic field is currently skewed by 1.8 degrees.
oh,
The software then instantly mathematically corrects the nonlinear inductance. It counteracts the magnetic mirage in real time, ensuring the calculated angle used by the inverter is always perfectly orthogonal to the true rotor magnetic axis. It uses math to cancel out the physics.
that is incredibly elegant. But the source document has one more design prevention, and this one really caught my eye because it involves adding completely new hardware. Search coils redundancy.
This is a fascinating addition. The engineers designed highly sensitive search coils and physically embedded them directly into the stator slots, perfectly aligned with the main windings.
Okay, I have to challenge this logic. The source says these search coils are highly sensitive, perfectly aligned, and they provide flawlessly clean back EMF data because they don't carry any of the heavy high-voltage load current. If they're so perfect, why do we even bother with the primary resolver? Why not just rip the complex resolver out, save the manufacturing cost, and use these search coils for everything?
It's a great question, and the answer comes down to the fundamental laws of induction, specifically Faraday's law.
Okay, take me back to physics class.
Search coils measure back EMF, but back EMF is only generated by a change in the magnetic environment, meaning the motor has to be physically spinning. When you are stopped dead at a red light on a steep hill and you need maximum instantaneous torque at exactly 0 RPM just to get moving without rolling backwards, the search coils produce exactly 0 volts.
Ow.
They are completely, utterly blind at 0 speed.
Because nothing is moving, no magnetic lines are being crossed, so no voltage is induced in the search coils.
Exactly. So the primary resolver handles the brutal heavy lifting for absolute position sensing at a standstill and during initial low-speed crawling. But once the motor is spinning fast enough, those decoupled search coils wake up.
And they don't have to deal with the heavy load current.
Right. Because they don't carry the massive hundreds of amps of driving current, their local magnetic field isn't distorted by saturation. They act as an incorruptible, pristine referee. If the primary resolver starts drifting due to heat, the search coils provide a pure position signal, enabling that 5-millisecond online ice test smoke correction we talked about earlier. They are the ultimate backup singer, stepping in exactly when the lead loses their voice.
Okay, so the design is utterly bulletproof on paper. We have step pins, lookup tables, and incorruptible referee coils. But a mathematically perfect design on paper can be ruined by a single tired worker on the assembly line or a poorly calibrated robotic arm.
Absolutely.
If the parts aren't built right, the design doesn't matter. Which means we need to look at PFMEA, process failure mode and effects analysis. How does a factory guarantee perfection when mass-producing 100,000 of these motors a year?
Well, the factory floor requires intense, unforgiving gating mechanisms. The source outlines several, starting with laser TR gating. We talked about that microscopic 0.05 millimeter tolerance limit for the rotor wobble. You cannot rely on statistical sampling to guarantee that.
Right, you can't just pull one out of every 100 motors and measure it and assume the rest are fine.
No. On the factory floor, they deploy high-precision laser displacement sensors on the actual assembly line. These lasers scan 100% of the rotor surfaces as they are built. They measure the dynamic runout, the TIR, in real time as the part spins on the assembly fixture.
And if a piece of dust gets in there, or the bearing is seated slightly crooked and the laser reads a wobble of 0.06 millimeters?
The machinery physically locks the assembly fixture. A red light flashes. The programmable logic controller of the line intercepts the part. It literally cannot move forward to the next station. It is a hard, physical, automated gate.
That's intense. But even if the rotor is laser perfect, the resolver still has to be bolted to the housing. Which brings us to a detail in the source that seems incredibly mundane at first glance. The phosphate-coated screws.
Right.
It mentions using OCR cameras and a torque angle tightening method. I mean, a screw is a screw, right? You put a robotic screwdriver on it and tighten it until the computer says it hits the target torque. Why is a chemical coating a critical safety gate?
To understand why this matters, we have to dive into engineering tribology, the science of friction. Tightening a critical safety component isn't just about applying a twisting force, which is torque. Torque is actually a terrible metric for tightness.
Like, really?
Yeah. What you actually care about is achieving the correct downward clamping force, stretching the screw like a spring to hold the parts together. This is known as axial preload.
Right, because if it's not clamped down hard enough, the vibration will back it out.
Exactly. To guarantee this preload, the factory uses two-stage closed-loop servo screwdrivers running a torque angle method. It measures how hard it's twisting, but it also measures exactly how many degrees of rotation the screw turns after it makes initial contact. But here is the massive catch. The equation for torque relies heavily on the K factor, which is the friction coefficient of the screw threads.
Let me guess. Bare metal screws have unpredictable friction.
Highly unpredictable. If you have a batch of bare steel screws, the friction varies wildly from screw to screw. The robotic servo screwdriver might spend 60% of its twisting energy just fighting the random friction of a dry, slightly rough thread.
Ah, I see where this is going.
Right. It hits its target torque limit and stops, but because it wasted all its energy fighting friction, the actual downward clamping force of the preload is dangerously low.
It thinks it's tight because it was hard to turn, but the resolver isn't actually clamped down, it's just stuck in the threads.
Precisely. And the moment that motor hits a pothole, the vibration overcomes that weak clamp and the resolver slips. So the factory mandates phosphate-coated screws. The phosphate coating acts as a standardized microlubricant. It locks in the K-factor. It ensures that 100% of the screwdriver's torque energy is converted directly into true downward axial clamping force. It removes the unpredictable friction variable entirely.
And because humans make mistakes, the factory doesn't just trust that the right screws are in the bin.
Right. They force optical character recognition, or OCR cameras, to visually scan every single bin of fasteners before the robotic arm is allowed to pick one up. The AI camera must visually read and confirm the words phosphate-coated on the supplier label. If the camera reads a batch of plain steel screws, the robot shuts down.
It's astounding that an AI camera reading a paper label about a microscopic chemical coating on a 1-inch screw is the very thing preventing a massive SUV from losing its mind at 80 miles per hour.
It's all connected.
But there is one more factory gate, and it's the ultimate digital padlock, the MES-EOL lock.
Manufacturing Execution System, end-of-line lock. At the very end of the assembly line, every single fully built motor is put onto a massive test bench and run at a microload. This is the factory proving ground. This is where the resolver offset learning, our sonar ping, must happen for the very first time.
So the system injects the high-frequency signal, calculates the zero offset based on the rotor saliency, and verifies it.
It verifies it against the rigid engineering tolerances. If the calculated offset is out of bounds, the motor fails. But more importantly, and this is a critical safeguard against the human software error we discussed in Root Cause 3, the factory network must take that unique, bespoke offset data and successfully upload it to the manufacturer's global cloud database, permanently tying it to the motor's serial number.
Why does it need to go to the cloud? Why not just leave it in the car's computer?
Because of the aftermarket mechanic 5 years down the line, if that motor ever needs a new inverter or a software wipe years later, the mechanic's diagnostic tool needs to pull the exact original factory offset data from the cloud to calibrate the new hardware. If the data isn't there, you get commutation data loss. So at the end of line test, if the motor fails the ping test, or if the factory Wi-Fi blips and the cloud upload fails, the MES system digitally locks the work order.
It just freezes the process.
It refuses to print the final factory barcode. Without that barcode, the motor becomes a ghost in the system. It physically cannot be scanned and bolted into a chassis. It is 100% intercepted at the source.
So we have mathematically flawless designs. We have solid steel step pins locking down 0.05 millimeter tolerances. We have AI cameras verifying phosphate-coated tribology. We have cloud-locked barcodes. It sounds invincible.
Yeah, it does sound invincible.
But in automotive engineering, sounds invincible is a dangerous phrase. You have to prove it. Which brings us to the final, most violent phase of the source document, DVP&R, production validation.
Design, verification, plan, and report. This is the final sign-off before a single motor is approved for mass production and sold to the public. You have to violently test everything you just built. You have to actively try to destroy it.
And the first test is the extreme mechanical fatigue testing, or as I look at it, the physical torture chamber. The parameters outlined in the source are just staggering.
They are. They take this perfectly assembled motor, put it into an environmental thermal chamber, and heat it until the entire core is thermally saturated at 150 degrees Celsius.
That is over 300 degrees Fahrenheit. The metal is expanding to its absolute limits. The magnets are deeply stressed. The air gap is warping.
Then, while baking at 150 degrees, they spin the motor to a massive overspeed of 18,000 RPM. They hold it at that screaming red line for 30 straight minutes.
18,000 RPM. The centrifugal force is trying to rip the resolver housing off the shaft. Trying to shear that steel step pin must be astronomical.
But just spinning fast is smooth. To really test slippage, you have to test violent changes in momentum. So after baking for 30 minutes at 18,000 RPM, they hit the motor with 100 extreme acceleration and deceleration impacts. The engineering specification demands an angular acceleration of 25,000 radians per second squared.
Let's pause on that number because 25,000 radians per second squared is really hard to visualize. For the non-physicists listening, that is an incredibly violent physical shock. That is the equivalent of a heavy mass spinning at top speed and essentially slamming a solid steel bar into the gears to stop it, reversing it, and slamming it again over and over and over.
Exactly.
It is designed to shatter the mechanical bonds. It is actively trying to snap that physical poka-yoke pin we praised earlier.
It is trying to find the weak point of the metal. And the success metric to pass this test is brutal. After 100 of those impacts at 150 degrees, the engineers take the motor out and measure it. The mechanical offset of the resolver must be less than or equal to 0.05 degrees. And the TIR, the physical runout wobble, must still be under 0.05 millimeters.
And if it shifts by 0.06 millimeters after all that violence?
The entire motor design fails validation. They go back to the drawing board.
So that's the physical beatdown. But what about the digital side? How do they test the software safety net? You can't safely test the limp home mode and that 720-volt stepwise ASC parachute by driving a prototype car at 80 miles an hour and throwing a wrench in the motor.
No, that would be lethal. Instead, they use HIL, hardware-in-the-loop fault injection. This is the digital torture chamber. They put the motor controller on a bench, hooked up to a real spinning motor running at 12,000 RPM under absolute full electrical load. It is pulling maximum current. Then the validation engineers use an FPGA HIL system.
FPGA being Field Programmable Gate Array, high-speed custom hardware.
Basically a high-speed, hardware-level hacker tool. They use it to instantly inject a fake 10-degree offset mutation directly into the resolver's data stream.
So they lie to the computer while it's running at top speed, simulating that a screw just snapped and the resolver slipped 10 degrees instantly.
Exactly. They inject the poison data, and they start the stopwatch. The success metric is entirely based on time and stability. The system's IST-SMO observer must recognize that the incoming data contradicts its internal math. It must catch the fault, abandon the physical sensor, and execute the limp home mode in under 60 milliseconds.
The 50i window we talked about?
Yes, but just catching it under 60 milliseconds isn't enough to pass. The transition from physical sensor to sensorless math must be incredibly smooth. The requirement states that the torque ripples during the switchover must stay below 5 Newton meters.
Torque ripple, meaning the physical jerk or shudder felt by the driver, has to be so small they barely even notice it, even though the motor just lost its primary sensor while pulling massive current at 12,000 RPM.
Precisely. And crucially, if they inject a severe enough fault to trigger the hard clamp, the controller must deploy those stepwise ASC short circuits perfectly, absorbing the massive energy spike to keep the DC bus voltage safely under 720 volts. No blown inverters, no fires, no exceptions.
The last test the source mentions is the MES escape pressure test. This sounds like they're testing the factory floor's digital locks, the cloud upload system we talked about earlier.
That's exactly it. They deliberately construct 100 bad manufacturing work orders. They take motors with uncalibrated RLLs, motors with corrupted zero-point data, and motors with the wrong software flashed to them. They try to sneak these 100 defective units down the assembly line to see if the MES system can be tricked into printing a barcode.
And the success metric, let me guess, 99%.
100% interception. The digital gates must block 100 out of 100 from printing barcodes. If 99 are blocked and just one single defective unit escapes the factory floor, the entire manufacturing control process is deemed a failure and must be rewritten.
What an incredible exhaustive journey. Just to recap for you listening, we started with the microscopic physics of why an EV motor loses its mind, the relentless mechanical slippage, the pole pair math that violently multiplies a 1-degree slip into a 10-degree crisis, and the invisible thermal saturation that bends the magnetic reality.
We then looked at how the software fights back. The sonar ping ROL handshake, the 5-millisecond digital immune system switching to pure mathematical observers to navigate in the dark, and the 60-millisecond active short-circuit parachute saving the hardware from a 720-volt meltdown.
From there, we looked at how designers use 0.05 millimeter geometric pins and decoupled search coils to prevent the failure entirely on the drafting table. We walked the factory floor to see lasers and phosphate-coated tribology locking down the assembly process. And finally, we threw the motor into an 18,000 RPM, 25,000 rads per second squared physical torture chamber to prove it all works.
It is a profound testament to modern engineering. The layers of redundancy, mechanical, software, factory, and validation are simply staggering.
It really is. But before we wrap up this deep dive, there is one final, incredibly fascinating detail buried at the very end of our source material that I want to turn your attention to. It mentions that modern engineering teams are now relying heavily on Python simulation tools. They are building massive transient mathematical models of these zero-point deviations against different motor pole pair ratios, like 8, 12, or 20 poles.
Yes, the creation of digital twins. By combining the electromagnetic finite element analysis with the control logic algorithms, they are perfectly calculating the maximum allowable offset error window in a purely digital simulated space. They are finding the exact point of catastrophic failure before a physical part is ever even cast in metal.
And that leaves me with a final thought for you to mull over. We've just spent all this time talking about the sheer unadulterated violence of the physical DVP&R tests, the 150-degree ovens, the 25,000 rads per second squared impacts. But if these mathematical models and Python digital twins are becoming so infinitely precise that they can dictate algorithm calibration limits for highly dynamic transient magnetic failures purely in code, are we approaching a future where those physical torture tests become entirely obsolete? Will the physical metal-bending beatdown of validation be replaced entirely by a massive simulation running silently on a server farm?
That is exactly the horizon automotive engineering is racing towards right now, a purely mathematical, simulated assurance of physical, real-world safety.
And it brings us right back to the stakes we started with. Passing a truck at 75 miles per hour requires absolute trust in the machine. For a long time, the mechanical reality of thermal distortion and physical slippage made that trust difficult. The diagnostic waters were muddy. But maybe, just maybe, these massive digital simulations and mathematical safety nets are finally giving us a perfect, incorruptible blueprint of the motor's soul. Thank you for joining us on this deep dive. Keep questioning the engineering around you, and we'll catch you next time.